Hi, welcome to another session of the Potter's Roundtable from Washington Street Studios in beautiful downtown Bolivar, West Virginia. I'm Phil Bernberg. Last time we talked about what happens in a glaze firing. That was the final session in our pottery making sequence. Today we're going to be discussing introductory chemistry for potters, the beginning of our next section on the use of raw materials.
Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
So let's get started. Introductory chemistry for potters. This is meant to be just sort of a little background information so that in some of our future sessions when we get into greater depth about glaze chemistry and some of the other properties of the clay and glazes, this is meant to provide a little more basic understanding. So chemistry is the study of the composition of the properties of matter, basically the stuff that everything is made of. And there are different branches of the science of chemistry that study different kinds of materials and different kinds of properties. For example, there's organic chemistry, which really is dealing with carbon-based compounds. There's inorganic chemistry, which is the division of chemistry, the science of chemistry, dealing with everything else, which is not primarily emphasizing carbon compounds. There's biochemistry, which is talking about the relationship between chemistry and life. There's physical chemistry, which deals with sort of the crossover between physics and chemistry. And finally, there's analytical chemistry, which talks about how you actually analyze things or determine the composition of materials and all the instrumentation and the techniques involved. Well, why do potters need chemistry? Basically because pottery or ceramics in general is chemistry at its heart. If you think about it, we're talking about clay bodies, and we need to understand the chemistry of the clay bodies. We're talking about glazes. When we burn fuels, we're employing chemical principles. So in essence, a major part of ceramics or pottery is chemistry at heart. So we need to understand chemistry really to make the best use of the materials that we're using and to solve problems, and really ultimately to be creative. The idea of all of this background information is to enable us to solve problems so that we're not tripping over them and stumbling on them all the time, and we can get at the goal, and that's to use our creativity. So let's talk about some basic chemistry concepts and some terminology especially. Okay, first of all, matter and atoms. Well, the universe is made up really of two things, matter and energy. And the matter, the stuff that makes up everything in the universe, is made up of the basic building blocks are atoms. And atoms, these atoms are tiny. For example, if you wanted to see the atoms in a baseball, you'd have to make the baseball the size of the earth, and then the atoms would be the size of grapes. So atoms are tiny, and yet and as we'll talk about it when we get into it further, even though they're infinitesimally small, they control all the properties of the materials that we see on our scale. The structure of atoms, we've really only known it confidently for about 100 years. There was a Danish physicist, Niels Bohr, who really refined and proposed the basic structure of an atom that we still use today. This was in around 1913. And this is just a diagram. This is a simplification of the way you can think about an atom. And it really consists of two major parts. It consists of a core, the nucleus, which is a very dense, heavy part of the atom. And the nucleus actually consists of two subatomic or smaller than atom particles, protons, which are positively charged, and neutrons that are neutral, that have no charge. And then circulating around or in a cloud or in orbits around the nucleus are the electrons, which are negatively charged. So what Bohr was proposing in the sense was that the atom you can think of it a little bit like a little mini solar system with the nucleus in the center and the electrons around the outside. And we'll come back to this. Especially we'll come back to these particles, protons, neutrons, that we'll use later on in some of our calculations. Well, there are three states or three forms that matter can exist in: solids, liquids, and gases. And in solids, basically, the atoms, we can think about them like this as little spheres or balls. And in a solid, the atoms are tightly bound together. So this is an example, my golf ball example. I had to wade into a lot of ponds to get these. This is basically an example, for instance, of what a solid might look like if you could look at it at very high magnification. The atoms are arranged, packed together in space, and they're rigidly attached, so they're really not free to move around. In a liquid, the atoms are still bonded together. They're attracted together, but the attraction is loose enough where they can move. So these atoms the golf balls in this jar represent a liquid. And so I can pour the liquid, and the atoms can move, but they're still attached to one another. They're not free to move separately. And then finally, in gases, the atoms in a gas are not attached. And so if this were a liquid and I would leave it open to evaporate, the atoms would be basically moving out of here and moving independently, and they're moving separately because they're not attached. So the three states of matter represent really different ways in which the atoms are attached together or bonded together. Now there are different kinds of atoms. There's not just one. This is the general schematic for it, but there are different kinds of atoms based on the number of the different kinds of particles that are in the nucleus and the number of electrons that are around outside. The term an element, when we say a chemical element, an element is matter that's made of one kind of atom. That is a particular atom that has a certain number of protons, a certain number of neutrons, and a certain number of electrons. And there are a lot of things in our environment around us that are essentially made up of elements. For example, aluminum foil, it may have some other ingredients in with the aluminum, but it's mostly pure, it's mostly aluminum. So when you see aluminum foil, or you see an aluminum cooking pot, or aluminum siding, you're really seeing the properties of that element primarily. Gold and silver used in jewelry, yes, they have some other materials alloyed with them, but basically you're still seeing primarily the properties of those elements, the gold and the silver. Lead is used in bullets, it's used in weights, it's used in fishing sinkers. Cast iron, of course, you see it in cast iron very commonly. Again, it might have some other little minor ingredients with it, but it's mostly pure iron. Mercury used to be used a lot in thermometers, still used in barometers. Carbon, very common. We see carbon as soot, either the black soot that's produced from a candle, for example, or a kerosene lantern. Also, that's produced by diesel exhausts. Every time a truck goes by and blows that smoke out, that's carbon. That's basically elemental carbon. And also, carbon is present as diamonds. Diamonds are basically pure carbon. Helium, used to fill balloons, that's an element. Copper, used again with maybe a few minor impurities, but making up copper wire used for electrical wire. So there are things in our environment around us that are largely or primarily pure elements. And so now let's get back to a little more terminology. The number of protons in the nucleus is called the atomic number. And every different element has a different number of protons in the nucleus or a different atomic number. And there are 92 different naturally occurring elements. That is 92 different kinds of atoms with 92 different numbers of protons and neutrons, everything going from 1 proton up to 92. But only about 30 of them are really common in the natural environment. The rest of them are pretty rare. The total number of protons plus neutrons in the nucleus is called the atomic weight of the atom. And both of these terms, especially the atomic weight, is used in Glaze calculations, which we'll talk about more later in this discussion. And we'll also talk about in future discussions where we go into greater detail on some of the Glaze chemistry. But to give you an example, aluminum is atomic number 13, but its atomic weight is around 27. Silicon atomic number is 14, and its atomic weight is around 28. So the atomic number is the number of protons in the nucleus. The atomic weight is the number of protons plus neutrons in the nucleus. Okay, let's talk a little bit about the periodic table. Just to introduce this concept. I have a copy behind me here. This is a copy of the periodic table. The periodic table is basically a chart that shows all the elements, the naturally occurring elements, as well as some that have been produced by man-made experiments. And basically, it's a chart showing all the different kinds of atoms. And if you notice, if you look at the chart, there are chemical symbols that are used to represent the elements. They're abbreviations, basically, because you wouldn't want to have to write out all the different symbols. Some of the symbols make sense. For instance, the symbol for silicon is Si, makes sense. Aluminum is Al. And some of them make no sense at all, at least on first glance. Like tin, for example, is Sn. Tungsten is W. And lead is Pb. And the reason why is because historically, as the atoms were basically discovered or recognized, they were given different names based on maybe people or places, and a lot of them are based on Latin or Greek names. So tin, Sn, for example, is based on stannus from the Latin. Tungsten is W because it comes from wolfram. Lead comes from the Latin for plumbum, Pb. So there's no, if you're interested in chemistry, and when you look at this chart, there's no specific logic to the names or the abbreviations. Basically, you have to memorize them. But on the periodic table, the elements are listed in order of increasing atomic number. That is, in the order of increasingly number of protons in the nucleus. So hydrogen, all the way over here, atomic number 1, has 1 proton in the nucleus. And you go all the way down to the bottom to uranium, which is 92, and that has 92 protons in the nucleus. Now, one of the really really useful things about this particular chart and the way the symbols are arranged is that the atoms are grouped so that where they appear on the chart, they have similar properties. So the atoms, for instance, in a column running down like this, all have basically similar chemical properties. And we know also when you look at the chart that there are certain regions of the chart that contain metals, like in here. Some of them have materials which are less metallic. They appear over here. Some of the gases appear over here. So they're not only are they listed in order of increasing atomic number, but they're grouped according to the properties, which is very useful. So in terms of our ceramics and our pottery, most of our ceramics are, at heart, they're aluminum silicates. So they're made up primarily of these 3 atoms: aluminum, silicon, and oxygen. And the first 2 columns in the chart, these basically list the materials that we use as fluxes in our clay bodies, but especially in our glazes. Fluxes are materials that help something else melt at a lower temperature. So lithium, sodium, potassium, we use as fluxes. And again, they're in a column, so the lithium, sodium, potassium all behave in a similar way chemically. These are called the alkali metals. And this next column, these are called the alkaline earths. So magnesium, calcium, strontium, and barium, that's another series of elements that we use in the form of fluxes for our materials. Our colorant, a lot of the colorants that we use in glazes are located here in the middle. Vanadium, chromium, manganese, iron, cobalt, nickel, copper, those are our colorants. And again, these all behave in a relatively similar way. The fluxes in the column behave in a similar way. So they're grouped. That's the nice thing about the chart. They're grouped together by properties. There's one more element that occasionally, actually we run into a lot in ceramics that doesn't really appear in this chart, and the symbol is this, and that's the element of surprise.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for The Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.
Let's talk next, let's go on to a little bit, talk about what happens if you combine different elements. If you take different elements and combine them together, you get what are called compounds. And actually, most of the stuff in our environment, most of the materials of the stuff around it are actually compounds. Salt and sugar, that's a compound. Water, that's a compound. It happens to be a liquid, but it's a compound of hydrogen and oxygen. Plastics are all compounds. Gasoline is a compound. Rocks are compounds. Minerals are compounds. Wood is made up of a multitude of compounds. The gases in the air, carbon dioxide, carbon monoxide, sulfur oxide, those are compounds. And us, we're mostly made of compounds. So the compounds, however, are different from mixtures. If I was able to take two elements and just sort of mix them together, and they didn't do it, they didn't interact, I'd still be able to look at the mixture and pick out individual atoms of one element or another. I haven't changed them. But when I create a compound, I change the properties of the materials so that the compounds have different properties from the elements that make them up. And there's a really good example of that. And that is, if I take sodium metal, which is here on the periodic table, sodium, and the symbol is Na, and if I combine that with chlorine gas, the symbol is Cl, and that's all the way over here on the periodic table. Now, sodium metal is a soft metal, a shiny silvery metal. I can cut it with a butter knife, and if I throw it into water, it explodes. Chlorine is a poisonous green gas that's a lot heavier than air. As a matter of fact, it was used as poison gas in World War I. So if I combine this explosive metal with this poison gas, what do I get? If I make the compound, I get that, which is table salt. So I've taken these two extremely, relatively hazardous materials and made something that's basically essential to all forms of life, salt. So the properties of this is what's really amazing about chemistry. When I combine these two elements and I bond them together to form a compound, the properties are completely different than the elements would have by themselves. And when the elements actually are combined to form this new product, that's what's called a chemical reaction. And there are lots of reactions that we have in our field of pottery or ceramics. For instance, when we're doing a bisque firing, compounds are breaking down, that is, reactions are occurring, and gases are coming off from the impurities, for example, in the clay. There's a change in the atomic structure of the clay. Atoms are moving around, materials are changing in the clay itself. During a glaze firing, all the ingredients in the glaze are reacting together, and they're reacting, and they're also melting and forming this new material, glass. I also have reactions that are occurring to form certain of the colorants in the glaze. And I'm also forming new materials when I get to higher temperatures, as we talked about last time in the glaze firing. I've got reactions going on in the clay, and I'm forming new materials in the clay. These are all chemical reactions that are happening. And then if I'm firing in a kiln where I'm burning a fuel, coal or wood or oil, then the actual burning of the fuel, that involves a whole series of chemical reactions. For example, if I have a kiln and I'm firing it using propane, I can show you as an example what the chemical reaction looks like when you burn propane. The formula for propane, this is propane. Propane is a chemical compound, and it happens to be a gas. So there's the formula for propane. And if I combine that with oxygen, so I'm going to say 5O2, that represents an oxygen molecule, and I combine that and I heat it up, what I get is 3 molecules of carbon dioxide and 4 molecules of water. So this is, when we're burning propane, this is just one of the reactions that's happening, but this is basically the overall change. I combine the propane with oxygen, that's burning, gives off heat, and the products are carbon dioxide and water. So I can write a chemical reaction, and all of these are compounds. And this format with the arrow is a chemical reaction showing that this now changes to that. Okay, Plus, and the last thing, of course, when I'm burning fuels is that not only are the fuels burning and producing all these chemical reactions, but now the products, the carbon dioxide or carbon monoxide, if that was produced here, is now reacting with the clay and the glazes, causing other chemical reactions to occur. Okay, so if you can imagine, if I've got 92 different possible elements, there's a lot of possible different chemical compounds that I can form. And what chemists have done over the years is that, to simplify it, they've basically grouped them, similar compounds together, and worked out a system for classifying the compounds. And we'll talk about that a little bit, because we run into these names a lot. So first of all, you could have compounds that only consist of 2 elements. And here are some examples. Oxides basically, simple oxides basically consist of a metal or something like a metal plus oxygen. And then there are sulfides. These are something plus sulfur. And then there are chlorides. Well, we just had an example of a chloride. That's something plus chlorine. So we just had the example of sodium chloride. That's a chloride. There are carbides. That's something plus carbon. Well, a good example of that, and we use these, is silicon carbide. We have silicon carbide kiln shelves. That's a carbide. Something happens to be silicon plus carbide. And then there are nitrides even. This is not all of them. These are just some of them. There are nitrides, which is something plus nitrogen. Well, you've probably heard of some of the later models or kinds of kiln shells are nitride bonded silicon carbide. That's silicon nitride bonded silicon carbide, glued together. Okay? So these are 2 elements, something plus oxygen plus something plus sulfur, and we run into these a lot. Matter of fact, most of the materials we deal are these. We'll talk more about it. Okay, so that's 2. Well, now I can have, and this list is on. This is not inclusive. This is just an example of some of the common ones. But there are also, now you can think of, okay, there are compounds that consist of 3 elements. And a good example are what are called carbonates. And the formula might look something like this. Something plus carbon and oxygen. And a really good example is whiting, a very common glaze ingredient, right? Which is also known as limestone, and that's calcium carbonate. 3 different atoms. So calcium plus, so the formula for whiting is 1 calcium atom, 1 carbon atom, and 3 oxygen atoms. So that's a compound of 3 different kinds of elements. Then there are sulfates, which is something plus sulfur and plus oxygen. And then maybe I'll put an X here because this number could change. Something plus sulfur plus oxygen, okay? And there are borates. You've probably heard of Gerstley borate. This would be something, typically, for instance, calcium plus boron plus oxygen. And ultimately, the one that we use a lot are silicates. So silicates are something plus silicon, Si, which is this guy right here, plus oxygen. And frankly, almost all of our clay and almost all of our glazes are in fact made up of silicates, as I mentioned before. Something, and in this case, I mentioned like the clay, in that case, the clay, this one here is aluminum. That's not the whole formula, but it would mean aluminum, silicon, and oxygen. But our glazes are also primarily aluminum silicates. So, in ceramics, we use a variety of different compounds as raw materials to make up our clay and glazes. We use oxides, we use carbonates, we use silicates, we use borates to make up our materials. But when we are making up our materials, the raw materials are identified by lots of different kinds of names that in some cases can be confusing. So in some cases, they might have a chemical description. They might, like calcium carbonate. Well, or they might give you the formula. It might be CaCO3. Or it might be called like a rock name. They might call it limestone. Same thing. Or they could call it kind of a historical name, Whiting. Whiting was actually named because when you grind up limestone, it gives you a white powder. If you add it to water and throw in a little animal glue, you've got something that makes things white. So there are lots of different names that we run across, especially if you look in the lists of ingredients for glazes, that may be any one of a number of different types of names. There are also commercial product names for some of these, like EPK is a brand name, basically, EPK, for a kind of clay. That stands for Edgar Plastic Kaolin. It's a kind of kaolin clay that's mined in Florida. And this is a brand name, kind of like Scotch tape or Kleenex. So when you see a recipe or you see this ingredient, you have to know what this brand name is. The same way when you see Kleenex, you have to know that it's a tissue. Or OM4, sometimes they're given their industrial products are just given really simple numbers, like OM4 is the name, is the identification for a kind of ball clay. Or Custer feldspar. That's a particular mineral. It's a chemical compound that's with the brand name that's mined in Custer, South Dakota. Okay, well, how is all this chemistry information used? Well, basically, we need this to understand how do you actually formulate clay bodies and glazes. If you're just buying somebody has done this. If you're buying a commercial clay body or you're buying a commercially prepared glaze, somebody has done this already to learn what ingredients they need to use, what chemical compounds to formulate that material. We can also use this information to understand the changes that occur in the clay and the glazes during firings. And finally, and ultimately, how to solve problems with clay and glazes. So let's talk about two examples of the way we might use this information related to glazes. Okay, so suppose if I wanted to make up a really simple glass. This is sodium silicate. That's a compound, sodium silicate, a really simple glass, and the formula is this, I believe. Yes, okay. So now, if I wanted to make that up, I could make it up using two other materials. I could make it up using sodium oxide and I'll put the formula down here. And to that, I could add some silica, which we should be very familiar with. And the formula is that. And if I combine these and react them, I get that. Okay? So if I write this equation or this formula, like one sodium oxide and this should be a 2, and one silica, you notice if you count this, when you write an equation like this, the number of atoms on the right is the same as the number on the left. There's nothing left over or nothing. So I've got 2 sodiums, I've got 1 silicon, and I've got 3 oxygens. So this is called a balanced equation. So this tells me that if I take that plus that, I get that. And the nice thing, I can look at this and I can say, okay, I see how many sodiums I need, I see how many silicons and how many oxygens, but suppose I actually want to make this, how do I know how much to weigh? So in order to do that, what I need to do is I need to figure out some way to go from counting atoms to weighing atoms, because the way we would make something up, we'd weigh it out. So I have to have some kind of a conversion between the number of atoms and the weight of the atoms, and we know what that is. It's called Avogadro's number. Avogadro's number. And it's a really, really big number. It's 6.02 times 10 to the 23rd. That's a 10 with 23 zeros after it. So it's 6, basically, if you forget the O2, it's 6 with 23 zeros after it. This says there are 6.10 atoms in a mole of something, and I'll explain what that is. A mole, this is beside being a little fuzzy brown animal that gets into your garden, chemically, a mole is the atomic or molecular weight or something expressed in grams. So let's give an example. If I have silicon and the atomic weight is, I'll round it off. The atomic weight is 28. So if I have 28 grams, that's the atomic weight in grams. If I have 28 grams of silicon, I have that many atoms of silicon. This is one of the fundamental principles of chemistry, is this Avogadro's number. So if I have the atomic weight or the molecular weight expressed in grams, that weight actually contains that many atoms. So now I can go from counting to weighing. And that's the basis for use this to actually, this is the use to calculate molecular. So I use atomic weights and molecular weights to calculate the actual weights that I need when I want to make something. A second example of how some of this information that we used is the following. There are two different formats for writing a glaze formula, for example. One is the standard recipe where you have a list of ingredients, usually given by weight percent. And these ingredients might be things like silica, feldspar, clay, and so forth. And later on, we're going to talk a lot more about these ingredients and what they really are in future sessions of this presentation. But that's the standard recipe that you see. And then there's also another way of expressing a glaze formula called the unity molecular formula, also called the Seeger formula. And in this way of expressing it, you show the numbers of molecules of something, kind of like that chemical formula I just showed. So the standard recipe we use to actually prepare the glaze, the unity molecular formula, or the Seeger formula, is a really very useful tool for understanding how a glaze works. If I look at the different proportions of the number of atoms, I can tell a lot about what that glaze does and how it performs. So it's very useful to be able to convert back and forth between the recipe and the unity molecular formula. And in order to do that, we need to use the atomic weights and the molecular weights. So that's part of that calculation that we use to do the conversion. Okay, well, so far, this discussion is really only meant to be a brief introduction, to give you a little introduction to some of the terminology, which we'll reintroduce later, and we'll use it again. But I hope it will be useful. If you're interested, I'd recommend, I have two books, even though I'm not promoting the books, I have two books that I'd recommend that would be good reading for you. The first one is The Elements by Theodore Gray. This is good because if you've never looked at chemistry before, it's basically a very visual guide to the elements. It actually shows you what they look like, and it tells you the properties of the elements, all 92 of them. And then another good book, which is just good for basic chemical principles, is Chemistry for Dummies. I've used this in some of the classes that I've taught, and the reason why I like it is it's divided into sections, so you don't have to read the whole book. You can pick out individual topics if you're interested in them and just read those particular topics. Okay? Well, we hope this discussion has been useful today. If you enjoyed it, please like it and subscribe to our channel and share it with your friends and other potters. This helps us our videos get found on YouTube. If you'd like to support our educational outreach efforts, go to patreon.com and consider becoming a patron and search for the Potter's Roundtable on the Patreon site. Also check for our website, www.hfclay.com. The next topic in the series will be Introduction to Glaze Chemistry, basically understanding glaze recipes. So thank you for visiting with us today, and we hope to see you next time.
The Potter's Roundtable is brought to you by Washington Street Studios and our patrons. If you enjoy the show, please subscribe, give us a 5-star review, and tell your friends. If you want to learn more about Washington Street Studios and shared studio memberships, please visit our website at www.hfclay.com. Thank you, and we'll see you again next time on the Potter's Roundtable.